All right, so hello. You're here again with another week of Math 2413 weekly reviews. So this week we are going to be looking at limits at infinity and an introduction to derivatives. So first things first, let's go ahead and start off with limits at infinity. So whenever we're looking at limits at infinity, what we're going to go ahead and do is first go ahead and define what we're going to think of as limits of infinity. So we're going to go ahead and start with our intuitive definition of limits at infinity. So we have our intuitive definition of limits at infinity. So what we're going to go ahead and say is we're going to go ahead and let some function f be defined on the interval a to infinity. So just any number a. All right, so we can now go ahead and say we can then let and then we can say that we have a limit as x approaches infinity and it equals some number L. Well, that's going to go ahead and mean that f of x is going to approach that value L as x gets infinitely large. So what does this mean when we think about this in terms of graphs and limits? So what we can go ahead and say is let's have a graph that looks something like this. And let's say it's going to go ahead and look like this. What they're saying is that as we go ahead and as these x values start getting larger and larger, we can see that it starts to actually go ahead and taper off at some point. And that is what we can go ahead and define as being our limit L. And it's also important to note that this definition up here can be applied to negative infinity. So yes, that can be applied to our limit as x approaches negative infinity of f of x. The only difference is that our interval is now defined from negative infinity to some a. And right here we can go ahead and see, let's go ahead and call this, we can go ahead and call this L sub 2, since in this case, so in this graph we have our L sub 1 up here. And we also have our L sub 2 down here. So we can see how these graphs are infinite. So as x gets bigger and bigger and bigger in one direction or another, it's going to go ahead and approach some finite value. So, and it's also important to note that the line y equals L is a horizontal asymptote as the limit as x approaches either positive or negative infinity of some function f of x approaches out. So essentially, if you have a limit approaching infinity in one direction or another, and it approaches a finite number, that itself is going to be a horizontal asymptote. So let's go ahead and do an example of this. Let's go ahead and find the horizontal asymptotes, or just any, or actually let's go ahead and make it a little bit more fun. Let's do all the asymptotes on the function 5 minus 2 over x squared. Okay, so let's go ahead and just pretend that let's go ahead and have a graph of this function. So this function is going to look something like this. So we have our 5. All right, and now that we have the shape of our function, let's go ahead and just define a couple quick things. So we're just going to go ahead and show you the graphic method for right now. And then I'll go ahead and actually go back to this problem and do this as a geographic method. As an algebraic method. So right here, we can go ahead and see that. On both sides of the graph, it's approaching this little orange line right here, and we're going to go ahead and say that this is y equals 5. We can also see that as it's going up, it's also approaching our y-axis. So right now we can go ahead and say that we have a vertical asymptote just based on the graph at x equals 0. And we also have a horizontal asymptote at y equals 5. So now let's go on to see how we can actually go ahead and solve for these limits in an algebraic method. So let's go ahead and think about this theorem. So we're going to go ahead and introduce a new theorem. So if we have some value r, and r is a positive rational value, such that we have some value, some x raised to the r is defined for all x's then we can say that the limit as x approaches infinity of 1 over x to the r is going to equal 0. So it's actually pretty easy to think about if we actually think about this both in terms of like a table and a graph. So for example, if we have a table, or we think about this, if we think about this as a table, just in an algebraic way, we can go ahead and see that this 1 is always going to stay the same. It's always going to go, that's just a constant value. That is never going to change. Meanwhile, we've already declared that r is going to be some positive value and be rational, and then we've already just said that our x is always going to exist. Well, if you have an x value that's being raised to a positive value, that's going to go ahead and keep getting bigger and bigger and bigger as you approach infinity. So we have that 1 on top that's constant, and then we have that denominator that's always getting bigger and bigger and bigger and bigger as we approach infinity. Well, then it makes sense that that's going to go ahead and that this total fraction is going to hit 0, because like this isn't a power function, but when you think about it, if we had 1 over 1 is bigger than 1 over 2, which is bigger than 1 over 3, and then so on and so forth. That's essentially what it's saying. As you increase that denominator but leave the numerator the same, that's always going to approach 0. But now we have to think about what happens if we don't have a 1 on the numerator. So let's go ahead and try this little example. Let's say we have the function f of x equals 2x over x minus 1. And now we need to go ahead and find the limit of f of x as x approaches infinity. So let's go ahead and work through how we're going to go ahead and solve this. So the first thing we're going to do is we're going to go ahead and divide both the numerator and denominator by the highest power. So what we mean by this is essentially, since we see that we have 2x to the 1 up here, and then we have x to the 1 down here, what we're going to go ahead and say is we're going to divide, is we're going to take 2 over x all over x, and we're going to go ahead and have that again in the denominator. We're going to have x minus 1 all over x. Because we're dividing both the numerator and denominator by the same thing, this is algebraically appropriate. So if we go ahead and do this, we now have, we're now left with 2 over 1 minus 1 over x. So now the next step that we're going to go ahead and do is we're going to go ahead and take the limits separately. And we can go ahead and do this because of our limit laws. So we can go ahead and say that we're taking the limit as x approaches infinity of 2, and we can take the limit as x approaches infinity of 1 minus 1 over x. So our limit as x approaches infinity of the function 2 is always going to be 2, since we just have a constant right there. Now if we take a look at this limit as x approaches infinity of 1 minus 1 over x, that 1 is always going to stay constant. So we can go ahead and say we have our 1 out of the way. And now if we take the limit as x approaches infinity of 1 over x, well, we defined in that last example, in that last theorem, that if we have a positive power right here, and a positive rational power in the denominator divided by 1, or really any constant, then that's going to approach 0. So we're going to get 1 minus 0 equals 1 for our denominator. And then our last step is going to go ahead and just be divide the limits. So essentially we got 2 in the numerator, 1 in the denominator, so we're left with 2 over 1 equals 2. Therefore, our limit of our entire function is going to equal 2. So let's go ahead and try this whenever we have some other ideas of what happens when we have varying degrees of and we have varying powers between our numerator and denominator. So let's try another example. And in this example, we're going to go ahead and have our f of x equals 2x squared plus 300 all over 4x cubed plus 1. And once again, we're taking the limit as we approach infinity. So what we can do is we can go ahead and follow those first 3 steps again. So we're going to go ahead and divide both the numerator and denominator by our highest power. So we're going to go ahead and have 2x squared plus 300. And we can see our highest power between these two. So on the numerator, our highest power is going to be x to the squared, and our denominator is x to the cubed, so we're going to go with our x to the cubed. All over 4x cubed plus 1 all over x cubed. So we can go ahead and move this and clean this up to where we're left with 2 over x plus 300 over x cubed all over 4 plus 1 over x cubed. The next thing we're going to do is we're going to go on to step 2 and take the limit of our numerator and denominator separately. So now we're going to have our limit as x approaches infinity of 2 over x plus 300 over x cubed. And right here, so we have that 2 staying constant and that x approaching infinity. So once again, we follow that theorem and we can say that that first part is going to be 0. And once again, the same concept applies for the second one. We have that 300 staying the same as that denominator gets bigger and bigger and bigger, then our overall total is going to get smaller, so we're getting 0 again. Now let's take a look at our denominator. So now we have our limit as x approaches infinity of 4 plus 1 over x cubed. So we're going to go ahead and get 4 for that first part, since y equals 4 is just constant, that's always just going to stay equals 4 no matter what. And then once again, we're going to go ahead and take that limit of 1 over x cubed is just going to be 0. So now we're left with getting 0 over 4, which is just going to be 0. So therefore, our final value is going to be 0. So now let's just try one more time and see what happens if we have a higher power in the numerator. So let's say that we're taking the limit as x approaches infinity of 5x to the 4th plus 3x plus 2 all over x squared plus 1. So we're going to go ahead and proceed with our steps. So we go ahead and we're going to have a higher power in the numerator this time with x to the 4th. So we're going to divide everything by that. It's where we get 5 over x to the 4th plus 3x squared, or just 3x, plus 2 all over x to the 4th over x squared plus 1 over x to the 4th. So now we're going to be left with having 5 plus 3 over x cubed plus 2 over x to the 4th over 1 over x squared plus 1 over x to the 4th. Let's go ahead and take our limits real quick. So now we have our limit as x approaches infinity of 5 plus 3 over x cubed plus 2 over x to the 4th is going to go ahead and equal 5 plus 0 plus 0, which is 5. And then our denominator, we're going to go ahead and get, for that first term, we're going to get 0, and once again, 0 for the second term. So now we are left with having, we get 5 over 0. So if we have our limit as x approaches to infinity of 5 over 0, or actually, let's rewrite it like this. We're taking our limit as x approaches 0. Let's treat it like this. We're taking our limit as x approaches 0 of 5 over x. Well, if we're dividing a constant by a smaller and smaller and smaller number, that resultant product is going to go ahead and get bigger. So therefore, that limit is going to equal infinity. Therefore, our final value is going to be infinity. So now that brings us to some general rules of thumb. Just some general rules when you have rational functions. So yeah, let's say we have a rational function, we're doing this. And we're going to go ahead and define this as saying that we have, in the numerator, let's just say our first and highest term is going to be a times x to the n, and our denominator is going to be b times x to the r. So now that we have some of those clarifications, we're taking our limit as it approaches infinity of a rational function, and we've defined how to start those general rational functions. The first rule that we're going to have is when n is going to be greater than r, that limit as x approaches infinity of that f of x over g of x is going to equal infinity. And this makes sense because if you think about it, if we have a higher power on the numerator, that is going to keep actually increasing faster and faster and faster than the denominator can. Therefore, it's going to approach infinity. Our second rule of thumb is going to be when n equals r. That limit as x approaches infinity of f of x over g of x is actually going to be a over b. This is going to be a over b coming from that back here. And once again, it sort of follows the same logic. Those are almost increasing at the same rate because we have that same power. So if you're at, once again, if we go back to that first example, if we're able to eliminate everything except for those first two highest powers, we are actually just going to be left with a ratio because that's just going to just be the general rate that's going to go ahead and change. And then the last one we're going to have is when n is going to be less than r. Then the limit as x approaches infinity of f of x over g of x is going to equal 0. So once again, similar logic, it's just that now the bottom is going to end up going a lot faster than the top. And since the bottom's going to, since that denominator is going to be growing faster and faster and faster, that's going to end up probably hitting that infinitely high value first. Therefore, that's going to overpower that numerator and end up giving us 0 as a final ratio. So, and it's also important to note that these general rules can be applied to when taking the limit of as x approaches negative infinity, but you must check your signs. Now, it's usually not going to be as much of an issue for rules 2 and 3, because 3, well, that's just 0. It doesn't matter. 2, you're mainly just going to have to worry about that a and b. However, for 1, you're definitely going to have to check it, because in some cases, even if you're taking a limit as x approaches negative infinity, you could still end up with getting a result of positive infinity. So you're just going to have to really double check those signs and think about the behavior of the graph at that point. Because, for example, if you have, so for the example, if you have an x to the 4 in the numerator and an x squared in the denominator, well, those are both always going to be positive, even if you're going to go ahead and take the limit as x approaches negative infinity. Now, if one of those was an x cubed, that would be a different story. So you just have to always double check and think about the behaviors of what's going to happen at that point in order to think about your sign. So now let's go ahead and think about one more scenario. What happens if we can't clearly tell what's happening? If, like, for example, if we're not exactly in that form that we just had. Like if we don't know what at what rate it's improving, it's increasing or decreasing. So we're going to have to go ahead and get a little bit more creative. So we're going to actually go ahead and do an example to show how we have to get creative. So we're wanting to take the limit as x approaches infinity of the square root of x to the 4 plus 2x cubed minus 1 over 4x squared plus 1. So now, because we have that square root in the numerator, that makes it a little more confusing. We're going to have to just be a little bit more careful and involved when we're trying to go ahead and solve for this. So we're going to have to get a little bit creative. So one thing that we can do is we can actually go ahead and multiply by the conjugate, just to kind of go ahead and eliminate that in the top, so we can get a better idea of what exactly we're doing. So now we're going to go ahead and take the square root of x to the fourth plus 2x cubed plus 1. We're going to multiply that times on both the top and the bottom. So now that we have that, we can kind of clean this up a little bit more. So we're now going to go ahead and have So we can actually go ahead and now clean this up a little bit more to where we can go ahead and get this x to the fourth plus 2x cubed. These two terms are going to be eliminated, minus 1. We're also going to go ahead and get 4x squared plus 1 times the square root of x to the 4 plus 2x cubed plus 1. So once again, we can actually now go ahead and see that at any point, our highest power is going to be this x to the fourth up here. So we can go ahead and divide everything that we have by x to the fourth. So now we're going to go ahead and be left with having 1 plus 2 over x minus 1 over x to the fourth. So now we have to think about distributing this down here. So what we're going to go ahead and have, so we're going to go ahead and be left down the denominator with having 4x squared times the square root of x to the fourth plus 2x cubed plus the square root of x to the fourth plus 2x cubed plus 4x squared. So one thing that we can do is we can actually go ahead and pull this down into the square root. We can go ahead and just take the square root of this, which is going to be, or wait, actually square this. Never mind, square that. That way when we pull it out, we can go ahead and say that we have so we can go ahead and say that we have 16 x to the fourth times x to the fourth plus 2x cubed, all square rooted. So now what we can go ahead and say is we can also divide everything in a square root by x to the 8th, because x to the fourth equals the square root of x to the 8th. So now down here, we now have 16x to the 8th plus 32x to the 7th. So now we're going to go ahead and have the square root of 16 plus 32 over x. And then in the second term, we're going to have plus the square root 1 over x to the fourth plus 2 over x to the fifth plus, now we're back back to x to the fourth, 4 over x squared plus 1 over x. So now let's go ahead and move a little bit more forward. So now we're taking the limit as x approaches infinity. So now we're left with, if we're looking at both numerator and denominator. So now in the numerator we're left with 1 plus 0 minus 0. And then the denominator, we now have the square root of 16 plus 0 plus another 0 coming from the second term plus 0 plus 0. This gives us 1 over the square root of 16, which is equal to 1 over 4. Now, this method seems kind of long and boring, so if you want to go ahead and, for example, in this case, you could have just started off by dividing x squared right here and x to the fourth right here, but this is a good idea just to show you how you can manipulate a function if you don't know exactly what's going on. So that should be, for now, my last example of go ahead and taking these. If we have more time at the end, I'll go ahead and maybe do a couple more examples for limits. But now let's go ahead and move on to the introduction of derivatives. We have now finally reached the name of the class. But before we move on to derivatives officially, we're going to have to do a little quick brief review of tangent lines and velocities since they're very much so tied into derivatives. So a couple weeks ago, we went ahead and said that our tangent line is related to our secant line. So our secant line, the formula for that, it was going to be, we defined it as being y1 minus y2 over x1 minus x2. Or if we're relating this to a function, it would be we're going to go ahead and get f of x minus y naught over x minus x naught. And then whenever we did that, we talked about trying to go ahead and move this value closer to 0, since a secant line is just kind of an approximation but doesn't tell us the exact tangent. So in order to do that, to get our tangent, we have to think about getting that difference between our x values smaller and smaller and smaller so we can actually get a really, really good approximation. So because of this, we're able to say that the slope of our tangent line was equal to the limit as x approaches x naught of f of x minus y naught over x minus x naught. So now that we go ahead, so now we kind of have that, we've already have that form that we can go ahead and mess with using limits. But there's another way we can do this to kind of make this a little bit easier on ourselves. It seems more complicated at first, but when you actually work with it, it becomes like it's less numbers and less things that you have to work with, and it's easier to actually be able to cancel things out overall at the end. So what we can go ahead and do is define, we can say that x minus x naught is going to be defined as h. So what we can go ahead and say, or we can also say that x naught equals some value a. So now we can also say that x minus a equals h. So what we can do is we can go ahead and manipulate this formula knowing that we have this difference. So what we can say is that we have our slope of the tangent line can now be equal to the limit as x approaches h of our initial a that we're looking at right now, so our f of a, which is the point we're trying to look at, plus h. And then because h is close to 0, that means we're really not moving very far away from that point, minus our initial point, f of a, all over h. Oh, wait, it's our limit as h approaches 0. I had a handwritten typo. So now that we have this out of the way, this kind of shows another way how we can go ahead and define our limit just using different terms. That way we can go ahead and just clean this up a little bit more. So now we can go ahead and think about this in terms of velocity now, since tangent and velocity are once again related. So what we can go ahead, beforehand, let's say we have a position function which gives us our position versus time. So we can go ahead and call that our position versus our time, or S of t. So we used to say, in the last one we established that our average velocity when given a position function was equal to our change in position over our change in time. Well, once again, similar to our tangent line problem, that just gives us an approximation, but what if we want to know what happens at a certain point? Well, we could always say and use sort of a secant line approach. So let's say we're going to find the position at t equals 1, but we only know what's going on at t equals 0 and t equals 2. We could use the secant line approach, but that only gives us an approximation, but we want to find truly what's happening at t equals 1. So we have to find an instantaneous velocity version. So what we can go ahead and do is define h as being our t minus our t naught. So what we can go ahead and say is that our instantaneous velocity of our function can be related using limits, once again, using that same formula we did, to where we have our limit as h approaches 0, and then we can go ahead and say that we have our function s of some function. We can go ahead and say t naught, or we can once again let t naught equal a. So we can go ahead and say that we have a plus h minus s of a all over h. So now let's actually go ahead and do an example trying to actually play with this velocity function. So let's go ahead and think about both our velocity and tangent lines. So actually, first thing I want to do instead is go ahead and do a quick tangent line problem, just so we can kind of get used to this. So we want to find the tangent line of the function f of x equals 2x squared plus 1 at x equals 0. So now let's go ahead and think about this. Now we can use, and this time we're going to use our new definition of a limit. So we're going to go ahead. So we know that this is our f of x, and then we can go ahead. Let's go ahead and find what our what our y value is going to be at this point. So if we have this, if we have x equals 0, we're going to have 0. If we plug that in, we get 2 times 0 squared, which is 0, plus 1, so we get 0, 1 as our point. So now let's go ahead and think about this in terms of our new formula. So now we get the limit as h approaches 0 of, so if we're having our f of a plus h, essentially what they're saying is we're plugging in different things. So what they're saying is instead of plugging in straight f of 0, we're actually plugging in 0 plus h for what we have up here. So now what we would say is we have our f of a plus h is going to be 2 times 0 plus h squared plus 1 minus, and then just our initial minus our initial value. So for example, our f of a is just going to be 1. And we're going to put this all over just plain h. So now think about what this graph is doing. So first thing we can do is go ahead and just clean some stuff up a little bit. So what we can go ahead and do is we can go ahead and expand this top part of the function to say we have 2. So now if we go ahead and square that out, 0 plus h, we get 0 squared, which is 0, plus 2 times 0 plus h. So once again, we get 0. If we just FOIL all this out, yep, 0 times h, 0 times 2, plus h squared, plus 1, minus 1. So now if we go ahead and divvy this out, we're left with just 2h squared. So now what we can do is we can go ahead and take the limit as h approaches 0 of 2h squared over h. So now that we have this, what we can go ahead and do is we can actually go ahead and get rid of this h and the denominator just by canceling it out. So now we're left with the limit as h approaches 0 of 2h equals 0. And we know since our m is going to be 0, since they want actual tangent line, what we can do is we can go ahead and plug that in. We know that when m equals 0, it's just a straight line. So we already know what that y value is. So what we can just say that our tangent line is just going to be y equals 1. So now let's go ahead and try another one that's going to be a little more complicated, since this time we're not going to go ahead and take it at x equals 0. Since x equals 0 helped because it was able to eliminate a lot of extra variables. But let's see what happens when it starts getting a bit more involved algebraically. So so this time we're wanting to find the tangent line of 3x cubed plus 2x squared plus x at the point 2, or well, when x equals 2. So let's just go ahead and find our point. So we're going to go ahead and say just at x equals 2, so we can just work on finding our point. So we know 2 cubed is going to be 8. So 2 cubed is is 8 times 3 plus 2 squared is 4 plus 2, so we're left with 24 plus 8 plus 2, which is 34. All right, so now we're going to go ahead and plug this into our function. So now what we're going to do is we're going to have our limit as h approaches 0, and then we're going to go ahead and have our f of a plus h, or in this case 2 plus h, which is going to go ahead and be so we're going to have 3 times 2 plus h cubed plus 2 times 2 plus h squared plus 2 plus h minus, actually what I'm going to do right now, we're going to change the powers on this because this is going to get nasty. We're going to change this to a 2. We're going to change this to a, and then we're going to change this to a 1, and let's just go ahead and eliminate this because since we're just starting out, I don't want us to get this to be really, really, really nasty. We can go ahead and maybe come back and do the original powers after this. This would change our initial y value, so we're going to end up getting 3 times 2 squared is going to be 12. And then we're going to get so we're going to get 12, and then 2 times 2 is going to be 4, 16. All right, so now that this is going to be a lot less nasty, we're going to just say this is going to be minus 16. All over h. So now that we're going to go ahead, so now let's go ahead and move forward. So what we're going to do is we're going to go ahead and say, and start distributing the numerator out, just to go ahead and just start getting somewhere with this. So what we're going to do is we're going to have 3 times 2 plus h squared, which is going to equal 3. So now if we FOIL this out, we get 2 squared, which is going to be 4, plus we're going to get 2 times h, so that's going to be 2h times 2 is going to be 4h plus h squared, which if we go ahead and distribute that out, we're going to get 12 plus 12h plus 3h squared. Yeah, that would not have been fun if we kept that cubic. So now let's move forward. And then we're going to go ahead and do, since this is just, we don't have to do anything with this, so we can just go ahead and add that back in. Since that's just distributing a 2, which isn't bad at all, we're going to get our limit as h approaches 0. Let's go ahead and plug everything in right now. 12 plus 12h plus 3h squared. So now we have 2 times 2. So now we're going to have 2 times 2 is 4. 2 times h is 2h. So we can just go ahead and plug that straight in. Minus 16. All over h. So the first thing we can see is we have a 12, a 4, and a 12, 4, and then a minus 16. So all of that can be canceled out. So now we're going to go ahead and get our 12h plus our 3h squared plus 2h all over h. So now we're going to get our limit as h approaches 0. So we have our 3h squared, we have our 12h and our 2h, which is going to be 14, all over h. Well, we can go ahead and cancel an h out from everything, so we can get h, and then 1. So now we're going to get 3h plus 14. If we take the limit of that, we are just going to get Rm equals 14. So now at this point, it would just be plugging everything back in. So now we're going to have once again, we have our, so let's go ahead and rewrite our function right now. So where we have f of x equals 3x squared plus 2x at 216. So now what we can go ahead and do is just plug in, and we've already determined that our m is going to be 14. So we can just go ahead and plug this in and get our point, and go ahead and do our point slope. So we're going to go ahead and have our 14 times our, so we have our x minus our 2 equals our y minus y naught, so y minus 16, 14x minus 28 equals y minus 16. So now we're going to have, move that 16 over to the other side, so where we get y equals 14x minus 12, and that is going to be our final tangent line for that point. So once again, we can do a similar thing with velocity. So we're just going to do a quick velocity problem before we move into actual derivatives. Derivatives should get a little more, hopefully derivatives will get a little bit more fun next week. It's just for right now, once again, it's just kind of showing you how the limit of it, how the limit definition works. So now we can go ahead, let's say we have our function, we have our s of t equals negative 16 t squared plus 28t plus 8. And we want to find velocity So this position function is describing some sort of projectile. So let's just go ahead and just say when projectile hits the ground. So if we know that this S of t is our final position, what we can do, if we're wanting to find it when it hits the ground, we can go ahead and set this position function equal to 0, to where we get 0 equals negative 16t² plus 28t plus 8. Well, first thing we can see is that we actually have a common factor. So we can go ahead and let's go ahead and pull out a -4, just so it's a little bit cleaner. So now we get 0 equals -4 times 4t squared minus 7 minus 2. All right, so next thing we can do is go ahead and we can factor this function out real quick to where we can get 0 equals -4, and then we can get, so we see that we have a 2 at the end, so we're going to get a 1 and a 2. All right, and we want a -7, so our 4 can be broken down into 4 and 1, or 2 and 2. Let's go ahead and do 4 and 1. And then we're going to go ahead and want a positive. So let's go ahead and try make this a minus and this a positive. Let's just see what happens. So we get 4t times -2, which is going to be -8, plus t, which is -7. We're good. So we're going to want the positive 1, so we're going to get, so we have a -1/4 and a positive 2 for our root, so we're going to get when t equals 2. So what we can do right now, luckily for this, we're just having to find our function. So what we can do is we can go ahead and move forward just finding that velocity, or in this case, it's sort of similar to what our m was when we were looking at our tangent line. So what we can do is we can take the limit as h approaches 0 of, so we're going to have -16, and then we're going to have our 2 plus h squared plus 28, 2 plus h plus 8 minus, and we already said that our final was going to be a 0. So all over h. So let's go ahead and move forward and go ahead and start distributing. So we know that in our numerator we're going to get in our numerator we're going to get -16. So we're going to get 2 squared, which is 4. 2h plus 2h is going to be 4h. Plus our h squared. Plus a 28. So we can go ahead and just distribute this. So we're going to get 28h plus 56 plus 8. All over h. Let's distribute out that -16 to where we get -64 minus 64h minus 16h squared plus 28h plus this 56 plus 8 is going to be 64 all over h. So we have a -64 and a 64, so that can go. So now we just have everything in terms of h and h squared in the top. So now we're taking our limit as h approaches 0. We're going to have -16 h squared. Up here we have -64 and 28. So that's going to go ahead and give us a value of -36. all over h. All right, so now we can go ahead and cancel out all of the h's that we have. So we have h right here, and two h's right here, which is going to give us our limit as h approaches 0 of -16h minus 36, which is going to be -36 for our final velocity. And this actually makes sense because if this is a projectile that's being thrown up and then being thrown down, because if you look at the graph, it's going to look something like this, so it goes up a little bit so we can see our positions moving up, and then it moves down. So if we're actually moving down at that point, it makes sense that our velocity is going to be negative. So now this brings us to the part we have all been waiting for, derivatives. So all this has been a build up to derivatives. So the first thing we want to do for a derivative, so just in general, what is a derivative? Well, a derivative is just a way for us to see our rate of change. Derivatives are just the study, and calculus in general is just the study of a rate of change. So what we can do now is we can actually go ahead and look at the limit definition of a derivative. Hopefully next week we should be able to mostly stop with limits and we can start getting to the actual fun derivatives, but we're almost there, guys. So now we're going to have our limit definition of a derivative. So whenever we look at, so let's think about in terms of our different ones that we've done. If we're thinking about a tangent line of a function, we're thinking about, okay, what is the slope of this function at that point? And we know that slope is going to be just the rate of change of a function. If we think about a velocity and position graph, about velocity in terms of position, velocity is just the rate of change of that position. So this derivative is just a way for us to go ahead, and this is how it ties back into our limit definitions. So our limit definitions of a derivative is we can go ahead and define our derivative, our notation, as being, as we're going to call it f prime. You just have this little mark right up here. We can say that f prime of a is equal to the limit as h approaches 0 of f of a plus h minus f of a all over h. So, like I said earlier, this is kind of how it ties back into velocity, and this is how it ties back into the idea of velocity and tangent lines. It all comes back to the same formula. Derivatives are just like a more general approach. Instead of saying, oh, we're just looking at velocity, oh, we're just looking at tangent lines, it's just a way to say, here's a general approach to our rate of change. And also it's important to note that this, since earlier we went ahead and defined h as being our difference between x and a, well, we can also just go back the other way if we wanted to and say that we have the limit as x approaches a of f of x minus f of a over x minus a. So yeah, that's just essentially saying that we're not going to plug random stuff. We're not going to go ahead and define h. This is just saying if we want to leave everything in terms of x rather than having to go do it in terms of h. So I'm going to go ahead and just do one more problem. Go ahead and just do one more derivative problem for right now. So what we're wanting to do is find what is the derivative of f of x equals the square root of 4x plus 2 at x equals 1. Okay, so first thing we need, so this is essentially just saying what's this, like we're wanting to define our rate of change, which is in a way what we said earlier is kind of being our slope of the tangent line at that point. So at x equals 1, we're going to have to go ahead and find our y. So at x equals 1, we are getting the square root of 4 plus 2. Actually, I'm going to change this to a 5. I'm going to change this to a 5, which gives a square root of 9. So we have our point as being 1, 3. Okay, so now let's go ahead and go back to what we were saying earlier. So what we can do is say that we have our limit, and this time, actually I think I'll stick with the h. I'll stick with the h because we've been doing the h. So we're going to do, if we have time, I'll try again with the a. Our limit as h approaches 0, and we're going to have f of a plus h, so that's going to be the square root of 4 times 1 plus h plus 5 all minus 3 over h. So this one, as you can see, is kind of in a different format than the one we had earlier, but that doesn't mean we can't still work with it. So what we're going to do is we're going to actually go back to our lovely friends conjugates, because we want to be able to rationalize and get this out of the top. So what we can say is we're going to multiply both sides by the square root of 4 times 1 plus h plus 5 plus 3, both numerator and denominator. So now in the numerator, we are getting, so we're getting square root of 4, we're just going to go and cancel this square root to where we're getting 4 times 1 plus h plus 5. You can see that these two terms are going to cancel out on top because of the plus and minus. So we can just say all minus 9 over h times the square root of 4 times 1 plus h plus 5 plus 3. So we have our limit as h approaches 0. So now what we're going to do is let's go ahead and distribute out everything on the top. So we're going to get 4 plus 4h plus 5 minus 9 all over h times that big square root function, 4 times 1 plus h plus 5 plus 3. So we can see we have a 4 plus 5 minus 9, which is all going to cancel out, where we get, so now we are left with just this 4h over h. So we can go ahead and cancel out these h's. So now we're left with our limit as h approaches 0 of 4 over the square root of 4 times 1 plus h plus 5 plus a 3. So now, even though we still haven't gotten rid of all the h's, we can actually still go ahead and move forward, because the thing we wanted to cancel out that h on the bottom, because that would get us 0 in the denominator. But that's not really what we're looking for unless we're trying to look for infinite limits, and that's not exactly what we're trying to do right now. So what we can do is we can actually go ahead and think about, and then so now we can think about, if we just go ahead and plug a 0 in right now, we're not going to get a 0 in the denominator. We're not going to end up with some sort of weird form like 0 over 0 or something wonky like that. So now we're just now at a point where we can move forward. So where we can now say that this is going to be 4 over, so we can essentially plug in this 0 for h, since this actually is a point that exists. So we get the square root of 4 times 1 plus 0 plus 5 plus 3, which is going to get us 4 over the square root 4 plus 5 plus 3 square root, that's going to be 4 over 3 plus 3, which is going to get us 4 over 6. So therefore, the derivative of f of x equals the square root of 4x plus 5 at the point 1, 3 is going to be 2/3. So just as a recap, so we've gone over exactly how we can go ahead and analyze limits at infinity, limits as x approaches infinity. And we've also looked at how tangent line and velocity and derivatives are all related, and how we can actually work with that limit definition of a derivative in pretty much the 3 main contexts that you would use them for. So slope, velocity, and just general derivatives. So have a good week, and next week we should be back with looking at more less theoretical and more fun derivative rules.